April 27, 1945, 15:20 hours. Interrogation room, British Second Army Headquarters, Northern Germany. Major Wilhelm Schröder had commanded fuel logistics for the Wehrmacht's 15th Army during the Normandy campaign and subsequent retreat across France. He understood petroleum warfare better than most German officers, the calculations of consumption versus supply, the vulnerability of fuel convoys, the mathematics that determined whether armies advanced or stalled. British intelligence wanted his assessment of Allied logistics capabilities, particularly regarding fuel supply during the breakout from Normandy. The interrogating officer spread photographs across the table. Aerial reconnaissance images showing strange cylindrical objects being towed across the English Channel. Ground photos of what appeared to be industrial pumping stations disguised as coastal buildings. Technical diagrams of pipeline cross-sections showing multiple protective layers. Schröder examined them with professional interest, assuming they documented some conventional fuel distribution system the Allies had employed in France. Then the British officer placed a map on the table. It showed pipeline routes running from the English coast directly to France, not following ships or coastal routes, but as straight lines across the Channel's seabed. Schröder studied the map, his expression shifting from interest to confusion to outright disbelief. "You're claiming you laid fuel pipelines on the Channel floor." His tone suggested he was being shown propaganda rather than operational intelligence. "That's not possible. The Channel destroys any fixed installation. Tides, storms, ship traffic, nothing survives on that seabed." The British officer's response was matter-of-fact. "We didn't lay them on the seabed. We laid them in it, protected by multiple layers of armor and flexible enough to move with the tides." The pipelines operated continuously from August 1944 through the end of the war. At peak capacity, they delivered over 1 million gallons daily directly from England to France. Schröder's face went through several expressions as he processed the implications. His entire understanding of Allied logistics had assumed conventional supply methods: tankers crossing the Channel, fuel dumps near the beaches, truck convoys moving petroleum forward. The concept of pipelines delivering fuel directly from England to the front lines bypassed every vulnerability his forces had tried to exploit. No tankers to sink, no convoys to attack, no beach facilities to bombard. Just continuous flow of fuel from sources the Wehrmacht couldn't reach. "We never knew," he said quietly. "We assumed you were bringing fuel by ship and truck. We targeted your supply lines constantly. We never imagined you'd simply pump it under the Channel like water through a garden hose." He paused, staring at the maps. How is this even possible? The answer to that question represented one of the most audacious engineering projects of the entire war, a solution so ambitious that even Allied planners initially dismissed it as fantasy. The problem that should have stopped D-Day. Military operations consume fuel at rates that challenge logistics even under ideal conditions. Modern mechanized warfare transformed petroleum from mere commodity into strategic asset that determined whether armies advanced or died in place. The D-Day invasion would bring unprecedented fuel demands. Thousands of vehicles landing on hostile shores with no existing infrastructure to supply them. The basic mathematics were sobering. A single American infantry division required approximately 40,000 gallons of fuel daily for routine operations. British armored divisions consumed even more, up to 100,000 gallons per day, during intensive combat. The initial invasion would put multiple divisions ashore, all requiring continuous fuel supply beginning immediately after landing. Within weeks, as the beachhead expanded, fuel consumption would reach millions of gallons daily, Conventional supply methods appeared inadequate before planning even began. Tankers crossing the channel represented obvious targets for German U-boats, mines, and aircraft. Even if tankers reached the beaches safely, offloading them required port facilities that wouldn't exist until weeks after the invasion. Fuel drums could be brought ashore by landing craft, but the quantities needed would require continuous shuttle operations that would overwhelm available shipping. Temporary pipelines from ships to shore were vulnerable to storms, combat damage, and the channel's notorious tidal ranges. German defensive planning explicitly counted on Allied fuel problems to limit any invasion's effectiveness. Wehrmacht intelligence assessments predicted that Allied forces would establish beachheads successfully, but then stall within days as fuel supplies became inadequate for sustained offensive operations. This assumption shaped German strategy: allow the landing, contest the beachhead, then counterattack once Allied momentum faltered due to logistics failures. British planners understood this German calculation and recognized that solving the fuel problem would be as important as winning the beaches themselves. Conventional methods might sustain initial operations, but couldn't support the sustained offensive tempo needed to break out of Normandy and advance into France. The solution would need to deliver fuel in quantities no army had ever managed, with reliability that weather and combat couldn't disrupt. The answer emerged from meetings between military planners and petroleum industry engineers in 1942. If conventional methods couldn't deliver sufficient fuel, perhaps unconventional methods could. Specifically, instead of shipping fuel across the Channel, what if it could be pumped directly from England to France through pipelines laid on the seabed? The concept seemed absurd. Underwater pipelines across 40 kilometers of open ocean through one of the world's busiest shipping channels, delivering military fuel under combat conditions. Yet the more engineers examined the idea, the more feasible it appeared. The engineering that made madness work. Operation PLUTO, pipeline under the ocean, required solving technical problems that civilian petroleum engineers had never confronted. Pipelines existed for land-based fuel transport, but nothing in commercial practice suggested they could function in the English Channel's environment. The engineering challenges were fundamental. Design pipes that could survive on the seabed for months, handle saltwater corrosion, flex with tides without breaking, withstand ship traffic overhead, and deliver fuel reliably despite temperature variations and pressure changes. Two distinct pipeline types emerged from the development process. The first, designated HAIS, Hamel pipe, Admiralty, Imperial Chemical Industries, Siemens, consisted of flexible steel tubing wrapped in multiple protective layers. The inner steel tube carried the fuel. Around it, engineers wrapped lead sheathing for corrosion resistance, then layers of paper and jute for insulation, then galvanized steel wire for strength, all sealed in a final coating of tar. The result was a 3-inch diameter pipeline that could bend without breaking and resist the channel environment's corrosive effects. The second type, called Hamel, after the engineer who developed it, used rigid steel pipe sections welded into continuous lengths. These pipelines were larger, approaching 4 inches in diameter, and could deliver greater volumes, but required more careful handling during installation. Both types were tested extensively in Scottish locks and the Thames estuary, with engineers deliberately subjecting them to conditions worse than the Channel would impose. The pipelines survived storms, temperature extremes, and simulated combat damage, proving the concept was viable. The installation method proved as important as the pipelines themselves. Engineers developed massive floating drums called conundrums, steel cylinders nearly 10 meters in diameter, that could carry dozens of kilometers of pipeline wound onto them like thread on enormous spools. Ships towed these conundrums across the channel while the pipeline unwound behind them, settling to the seabed as it was paid out. The installation could proceed at several knots, meaning a complete pipeline could be laid in less than a day if conditions permitted. The pumping stations required equally innovative engineering. On the English side, engineers converted existing petroleum facilities and built new ones disguised as innocent coastal structures. One major pumping station was hidden inside what appeared to be a seaside garage. Another occupied a building that locals believed was an ice cream factory. The disguises were necessary because German aerial reconnaissance photographed the English coast constantly, and any obvious military-industrial facility would have invited bombing raids. The French side presented different challenges, since pumping stations couldn't be built until after the invasion succeeded. British engineers prepared mobile pumping units that could be brought ashore and operational within hours. These units connected to the undersea pipelines through flexible hoses that could be deployed by landing craft. The entire system was designed for rapid establishment. Pipelines could be operational within weeks of the initial landing, rather than requiring months of construction. Testing revealed limitations that required tactical adaptation. The pipelines couldn't deliver unlimited volumes. Their diameter and length restricted flow rates. Engineers calculated that each pipeline could deliver approximately 300,000 gallons daily under optimal conditions. Meeting projected fuel demands would require multiple parallel pipelines, which meant multiplying the already substantial engineering effort. Additionally, the fuel needed pressure regulation to prevent pipe rupture, requiring sophisticated pumping equipment that could adjust output based on system feedback. The technical solutions worked because British engineers approached each problem systematically. Corrosion, multiple protective layers, flexibility, careful material selection, installation speed, conundrum deployment systems, disguise, camouflaged facilities, limited capacity, multiple parallel lines. The cumulative result was a system that could function reliably despite operating in conditions that conventional engineering wisdom said should destroy it, the secret that Germany never discovered. Security surrounding Operation PLUTO was extraordinary even by wartime standards. The entire project operated under cover names and compartmentalized information sharing. Workers building components often didn't know what they were constructing. Pipeline sections were manufactured at dispersed facilities rather than central locations. The conundrums were built in shipyards and immediately moved to secure anchorages where German reconnaissance couldn't observe them clearly. German intelligence failed to penetrate Pluto's security completely. Luftwaffe reconnaissance photographed the conundrums but misidentified them as some type of floating breakwater or harbor defense structure. The disguised pumping stations appeared to be civilian facilities. The pipeline manufacturing was dispersed enough that no single intelligence report revealed the project's scale. Most critically, German planners simply didn't imagine that such a system was possible, which meant they weren't specifically looking for evidence of it. The assumption that underwater pipelines couldn't function in the channel was near universal among German military engineers. This wasn't ignorance, it was reasonable technical assessment based on available information. No commercial pipelines operated in conditions remotely comparable to the channel. The engineering required would be enormous. The vulnerability to storms and combat damage appeared prohibitive. German assessments concluded that even if the British attempted such a system, it would fail within weeks of installation. This technical skepticism provided perfect cover for British security. Even when German forces captured documents mentioning fuel pipelines, They assumed the references described conventional beach-to-shore systems rather than cross-channel installations. When German reconnaissance observed pipeline-laying operations after D-Day, they categorized them as local distribution networks supporting beach operations. The concept of pipelines running from England to France simply didn't register as plausible to German intelligence analysts. The compartmentalized nature of the project also limited security risks. Pipeline installation crews knew they were laying fuel lines, but not the system's full scope. Pumping station operators understood their facilities were important, but not how they connected to broader operations. Even within British command structures, knowledge of Pluto was restricted to those with operational need to know. This meant that if German intelligence did capture someone with Pluto knowledge, that person could reveal only their small piece of the system, rather than compromising everything. August 1944, when fuel began flowing beneath German positions. The first Pluto pipeline became operational on August 12, 1944, more than 2 months after D-Day, but well before Allied forces broke out of Normandy. The initial system connected Shanklin on the Isle of Wight to Cherbourg, running 100 kilometers across the Channel's seabed. British engineers had waited for Cherbourg's capture before activating the system, understanding that protecting the French terminal required secure territory around it. The first fuel delivery through Pluto was deliberately low-key. Engineers gradually increased pump pressure while monitoring the system for leaks or failures. The pipeline performed exactly as designed, delivering fuel steadily despite the channel's notorious conditions. Flow rates started conservatively, around 100,000 gallons daily, as operators gained confidence in the system. Within weeks, as additional pumps came online and operating procedures were refined, delivery rates increased substantially. By September, multiple Pluto pipelines were operational. The initial Cherbourg line was joined by additional routes to different French terminals as Allied forces advanced. Each pipeline operated independently, meaning failure of one line didn't compromise others. The system delivered fuel continuously, 24 hours daily, regardless of weather or sea state. The only interruptions came from scheduled maintenance or rare equipment failures, and even those were brief because British engineers had designed redundancy into every critical component. The psychological impact on British logistics planners was immediate and profound. For the first time in the campaign, fuel supply exceeded demand. Truck convoys that had been rationing petroleum carefully could now draw fuel freely. Armored units that had limited operations to conserve fuel could operate at full tempo. Aircraft that had reduced sortie rates due to fuel concerns could fly more missions. The bottleneck that should have limited Allied operations simply didn't exist because Pluto provided steady flow that weather and German attacks couldn't interrupt. German forces remained completely unaware of why Allied fuel supplies seemed inexhaustible. Wehrmacht intelligence documented constant Allied fuel consumption and tried to identify the supply sources. They noted tanker traffic across the Channel, but calculated that observed shipping couldn't account for the fuel volumes Allied forces were clearly using. The discrepancy confused German analysts who concluded either that their shipping observations were incomplete or that Allied forces had developed more fuel-efficient vehicles than intelligence had reported. The reality that Britain was pumping hundreds of thousands of gallons daily through underwater pipelines never occurred to German intelligence. Even when local French civilians observed pipeline terminals and reported them to German forces, the reports were dismissed as describing routine military infrastructure. The concept was too far outside German operational expectations to be recognized even when evidence appeared. The moment German planners understood They'd been beaten by engineers. German discovery of Pluto came gradually during the war's final months as Allied forces advanced into Germany and captured Wehrmacht logistics officers who'd fought in France. British and American interrogators began asking detailed questions about German fuel supply assessments, and German officers provided candid answers about their logistics calculations and assumptions. Multiple interrogation reports documented German officers expressing shock when shown evidence of Pluto operations. The reaction pattern was consistent. Initial disbelief that underwater pipelines existed, followed by recognition that this explained Allied fuel abundance, culminating in acknowledgement that German planning had failed to anticipate British engineering capabilities. One Luftwaffe logistics colonel stated during interrogation, "We knew British industry was strong. We didn't realize British engineers would attempt projects we dismissed as impossible. The pipelines explain everything we couldn't understand about Allied supply operations." The technical sophistication impressed German engineers who examined captured Pluto documentation after the war. One German petroleum engineer who reviewed the system's design specifications noted, "The engineering is elegant. Every problem has a practical solution." The British didn't develop revolutionary new technologies. They applied existing engineering principles systematically to solve a problem we thought had no solution. That's more impressive than technical innovation. It's disciplined problem-solving at massive scale. German strategic assessments, written after the war, repeatedly cited Pluto as example of Allied logistic superiority. Wehrmacht analysts acknowledged that German planning had underestimated Allied engineering capabilities and overestimated the constraints that conventional logistics would impose on Allied operations. One post-war analysis stated, "We planned to fight a conventional mechanized war where logistics limitations would restrict Allied operations. The British fought an engineering war where technical innovation removed limitations we counted on." Pluto exemplified this approach: identify a problem, engineer a solution, implement it at scale. Germany lacked either the resources or the imagination to match this capability. The psychological dimension was equally significant. German officers who learned about Pluto after capture expressed a sense that they'd been fighting an enemy more capable than they'd understood. The realization that British forces had operated with unlimited fuel supply while Wehrmacht units had rationed desperately created recognition that Germany had been comprehensively outmatched in industrial capacity. This wasn't merely losing to superior numbers, it was losing to superior systems, thinking, and engineering execution. The pipelines that won by never being noticed. The greatest success of Operation Pluto was that it worked continuously without German forces ever understanding what was defeating them. The pipelines lay on the channel floor, invisible and invulnerable, delivering fuel that kept Allied armies mobile while German forces struggled with chronic shortages. British engineers had created a strategic asset that couldn't be attacked because the enemy didn't know it existed. This invisibility was intentional and carefully maintained. The pipelines themselves were camouflaged by the seabed. The pumping stations were disguised as civilian structures. The operational security prevented information from reaching German intelligence. Even after the war, many veterans of the Normandy campaign didn't know Pluto had supplied them. They'd simply drawn fuel from distribution points without questioning where it originated. British engineers built the pipelines anyway, laid them on the seabed, pumped fuel through them continuously for 9 months, and proved that impossible was just a word that meant requires engineering we haven't done yet. The pipelines won by never being noticed until after the war was already lost. That was their genius. Not that they were technically brilliant, but that they were practically invisible while remaining operationally essential. German forces fought British armies that never ran out of fuel, never understanding that the fuel was being pumped from England through pipes lying beneath the channel they'd crossed to invade France. And by the time German officers learned the truth in interrogation rooms across occupied Germany, it was far too late to matter. The war was over. The pipelines had done their work. Britain had proven that sometimes the most devastating weapon isn't a gun or bomb, but a well-engineered solution to a problem the enemy assumed had no solution.